Now, B is uniquely equal to B row plus Bn by the direct sum, by the properties of matrices as they give you row spaces and null spaces. It follows immediately that if we subtract B from B row, we're going to get negative B sub n. Be sure you convince yourself of that. It's just straightforward algebra. And B sub n is a member of the null space of A transpose. So what we want, well, what do we want? We want to find the B row that corresponds to this B vector. Remember, this B vector is just this one in this case, whatever vector we have here, vector of our y values. We want the B row for that vector because that B row is what we get when we take our desired x, the x value that makes AX as close as possible to the B vector, to map onto B row. So that means that B row is going to equal AX for the x that we want. So what we want then is, instead of B row minus B being in the null space, we want AX to be our B row. So our condition for the x that we want is that AX minus B be a member of the null space of A transpose. This space here, the space that's orthogonal to this one. Okay. Well, I state this a little different. I say AX is closest to B when AX minus B is in the null space of A transpose. Just this condition. Now, what do we make of that condition? Well, if this is in the null space of A transpose, then if we multiply this vector by A transpose, we should get the zero vector, because that's what it means to be in the null space. Okay, well, that happens then when AX minus B is in the null space, which means that A transpose times AX minus B is equal to the zero vector. Well, we're home practically free now. If we have our matrix A, of course, it's very easy to get A transpose, and here we do have our matrix A, and we can easily transpose this matrix. We know what our B vector is. The only thing we don't know is what our X vector is, and this is a vector equation that we can easily solve for X. Okay, well, let's go through how we solve it. Well, if this is the case, then, well, by distributivity of matrix multiplication, this is just A transpose times AX minus A transpose times B that has to equal the zero vector, meaning that A transpose times AX is A transpose times B. Now, I'm not even sure that we can see everything over here. We can see everything I'm talking about right now, but let me shift the camera slightly so we can see everything that's been written out here toward the bottom. Okay. Okay, so again, this equation is just equivalent to this equation, and that's very straightforward, but make sure you understand why. Again, and I repeat, A is known, B is known, so this yields a system of equations that we can easily solve for X. X equal to A, B, C. Okay. This is going to be a system, in this case, of 3 equations and 3 unknowns. Why 3 equations? Well, A is 5 by 3. A transpose is 3 by 5. If you want to, go ahead and write them down and convince yourself that the product is going to be 3 by 3. I could make a side comment here. If A is M by N, then A transpose is N by M, so A transpose A is M by M. In this case, that would be 3 by 3. So in this specific case, we have a 3 by 3 matrix times X that's equal to A transpose times B. Now A transpose is 5 by 3. So A transpose times B is going to give us a vector of length 3. This means that in this case we're going to get 3 equations and 3 unknowns, and we simply solve those equations for x. That gives us the A, B, and C. That gives the best fit for y equals AT squared plus BT plus C.